Welcome to NASA Science Live. I'm your host, Joy Ng, and today we will talk to NASA experts about the sun, the most recent solar storms, and how our Parker Solar Probe mission will make history with its closest pass to the sun. This is your chance to interact with NASA experts and have your questions answered in real time. So be sure to send them in using the hashtag AskNASA in the comments wherever you're watching. In 2021, NASA's Parker Solar Probe became the first spacecraft to fly through the sun's upper atmosphere, known as the corona. This was the first time any spacecraft had touched a star, providing humanity with unprecedented observations, visiting the only star we can study up close. Now, Parker is about to complete one of its most daring feats yet. On December 24th, 2024, Parker Solar Probe will fly just 3.83 million miles above the sun's surface. If the distance between Earth and the sun was the length of a football field, Parker would be around 4 yards from the end zone. At the closest approach, the spacecraft will be hurtling around the sun at around 430,000 miles per hour. That's fast enough to get from Philadelphia to Washington, D.C. in 1 second. This makes Parker the fastest human-made object in history, and it's going to be an amazing achievement. We're keeping an eye on the questions pouring in online, and we'll bring them straight to our experts live on air later on in the show. We also have experts in the comments standing by to answer you in real time. So let's jump in. With us now is Dr. Alex Young, who is the Associate Director for Science Communications in NASA Heliophysics, and Dr. Noor Ralfi, Parker Solar Probe Project Scientist at the Johns Hopkins Applied Physics Laboratory. Thank you both for being here.
Thanks for having us.
Thank you for having us.
So can you start by explaining a little bit about your roles? Alex, why don't you go first?
Yes, I am, as you mentioned, the Associate Director for Science Communication in the Heliophysics Division at Goddard Space Flight Center. I'm also a solar astrophysicist studying activity on the sun and many of the aspects that Parker Solar Probe is now exploring in unique ways.
And I'm Noor Ralfi. I'm also a solar astrophysicist from the Johns Hopkins Applied Physics Lab. I am the Parker Solar Probe project scientist, and my primary role is the integrity of the science of the mission, but also maximizing the science return of the mission as much as possible.
Thank you both. So let's get into today's main topic, Parker Solar Probe. I mentioned earlier that it's getting ready to make its closest approach to the sun ever in history. Can you explain, why are we doing this and what do we hope to learn?
A star like our sun is by nature a very complex and dominant object. Numerous phenomena are so mystifying. And just to give you a couple of examples, the solar corona, that is the outermost layer of the solar atmosphere, is over 300 times hotter than the solar surface. That is mind-boggling. That boiling gas that is in the solar corona obviously cannot stay static. And there is a constant flow of charged particles that we call the solar wind. It is constantly rising from that region to fill the whole heliosphere. And the mystery about it is that the particles rise from a near static state close to the sun to be flying at hundreds of kilometers per second. And we don't know where do they get the energy from. And obviously the sun is a magnetized star. Every now and then, it shows us the violent side of a star through big explosions like coronal mass ejections and flares. Just to give you, to put this, the energy amount that the sun releases in minutes and hours, one of these strong events can fulfill our energy needs of the whole current civilization, our current civilization, for nearly 40,000 years. And the sun does that in minutes to hours. Along with this tremendous energy release, there are particles that get accelerated to almost the speed of light and rendering them a formidable hazard to humans in space, to space equipment like the GPS and communication satellites. And every now and then we see a show here around us like Aurora. But let me tell you this. Parker Solar Probe will help us address all these three phenomena, and that's actually why we primarily built it. But Parker Solar Probe is way more than that. It is an exploration mission by excellence. It is venturing into a region of space that we never visited before. And whatever observation we make is a potential discovery, and that is exactly what we're learning from the data.
So at Parker's closest approach to the sun, the front of the spacecraft will face temperatures approaching 1800 degrees Fahrenheit or 1000 degrees Celsius. But the spacecraft's instruments behind the shield will be near room temperature at about 85 degrees Fahrenheit. Can you explain how that's possible?
Yes, so this is one of the aspects of Parker that makes it an engineering marvel. And my colleague Noor here has something really special. This is a piece of the heat shield that sits in front of the spacecraft. It's made of a carbon composite fiber, and you can see it's fairly thick. It sits in front and always faces the sun, and it completely covers the back part of the spacecraft. It casts a shadow over the instruments at the back, except for one specific piece left. And that is one of the parts that keeps this immense heat from damaging the instruments. But in addition, engineers have created a type of radiator that amazingly uses only a gallon of distilled water. And together, that with the heat shield allows us to keep enough heat away or siphon heat off of the spacecraft to keep that nice cozy room temperature back where these really important science instruments are.
Wow, that's incredible that it can be so close to the sun, yet we've developed new technology to maintain a safe operating temperature. So to celebrate this amazing feat, we have a challenge for you. You can join Parker's journey with a digital quest of your own. So starting today through December 24th, NASA will post a daily puzzle on the NASA Sun Facebook and X accounts. Solve these puzzles to find secret NASA web pages where you can claim your own custom 3.8 digital stickers. Let's learn more.
NASA's Parker Solar Probe is about to make history. On December 24th, it'll pass within 3.8 million miles of the sun's surface while traveling faster than any human-made object in history. And we want you to join in on this historic event. Each day from December 17th to the 24th, we'll hide a prize on a secret webpage and share clues across social media to help you find it. Solve the clues to win your prize, but hurry and you can also claim glory. Clues drop at noon Eastern Time each day. And at 9 p.m. Eastern, we'll share the leaderboard showing who solved that day's puzzles the fastest. Then, on December 27th, when Parker phones home for the first time, letting us know it survived the sun's intense heat, we'll release a final leaderboard showing who solved the puzzles fastest overall. Are you ready for the 3.8 challenge?
So Alex, Noor, are you ready?
I'm ready. I just hope that I'm not a complete failure at all the puzzles. So
I'm ready to play.
So today's puzzle has been released. So let's show that now. The goal is to guess what this drawing is showing, and the answer should be 2 words. To find the secret webpage, you just have to put the answer at the end of the URL, which is go.nasa.gov/3.8_ and then the puzzle answer. And the fastest puzzle solvers can also compete for a space in our leaderboard. So good luck to everyone. And clues we posted on the NASA Sun Facebook and X accounts. But I guess for you, Alex and Noor,
I think I have a good idea.
If you have a good idea, don't say the answer live on air. But if you can guess, go put it at the end of that URL you just saw.
Okay. So
Parker has a total of 3 planned orbits at this record-breaking distance from the sun. So my question to you two is, are these flybys occurring during a specific period of activity for the sun?
So we launched Parker Solar Probe in the summer of 2018, and back then, the sun was at solar minimum, the minimum of the solar cycle. It was very quiet. And if you think of it, a mission that is going close to a star where the medium is by nature very complex, it was the best time, the perfect time to have Parker Solar Probe flying close to the sun. And the reason for that, we will learn about the simplest state of the solar corona and the solar wind. And as the solar activity rises, we will start learning about the complexity that is building up in the system. And now we find ourselves so fortunate to be at the solar maximum when Parker Solar Probe is hitting the closest approach ever to a star. And we want the sun to give us the biggest show it can do when Parker Solar Probe is very close to it.
That's fascinating and amazing that the mission had planned the timing of this with the sun's activity. So one of the effects of the sun's activity...
I can actually add one thing. Thing to that. One of the things that's fantastic about Parker being such a robust spacecraft and the fact that we're going to be getting data for many years to come is we will have Parker over a solar cycle. And it is very important for solar science to study various aspects of the sun over both the minimum and the maximum, as well as the transitions between. So this is really exciting that we'll be able to combine Parker's data with the huge heliophysics observatory to have this unique perspective over an entire solar cycle.
So, Alex, whenever you speak, you trigger this idea in my mind. So let me say this. Let me say this. After more than 6 years of orbiting the sun very closely, Parker Solar Probe and all the subsystem are performing way better than we expected. Also, the continuation of the mission is a NASA decision. As Alex said, Parker Solar Probe is ready to go for many years to come.
Yeah, it's amazing that Parker is there right now during the active sun. And for our viewers watching, you may have seen some of the visible effects of the sun on Earth, which is the aurora. And we've seen a lot of aurora this year, especially in the lower parts in the US, which is not typical. So can you explain what is an aurora and why did it appear in places that it doesn't usually appear?
Yeah, so all of this material and magnetic field in the form of the solar wind or also the coronal mass ejections, it comes through space and hits everything and interacts with everything that's in its way. And when the Earth is in its way, it interacts with the Earth's magnetic field and jostles it like a bell. And one of the things that causes is it causes particles both from the Earth itself as well as from the sun to stream down the magnetic field lines of the northern and southern poles of the Earth. And when that happens, these particles interact with our atmosphere, which is primarily oxygen and nitrogen. And so when these particles with a lot of energy, primarily electrons, hit oxygen, they create, depending on how energetic they are and where they are in the atmosphere, they can either create these beautiful greens or sometimes these very vibrant reds. And the nitrogen will create a blue, sometimes a teal, and together that is what's giving us this really amazing rainbow of colors that's producing this amazing show. And one of the things that's been really special about this year is we've actually had 2 solar storms that have caused aurora here at Earth. One was in the beginning of May, and one was in the beginning of October. And both of those storms caused aurora to be visible down to the very bottom of the United States. But the May storm was an especially strong storm. In fact, we think it could be 100 to possibly 500-year event. And that caused aurora very close to the equator, which is extremely unheard of. And it was a worldwide event that millions and millions, hopefully billions of people were able to see. And it may not happen again, but as Noor said, I'm hoping the sun keeps up this activity, gives some excitement to Parker, and maybe we get a little bit of that excitement here at Earth and have some more spectacular light shows.
Parker Solar Probe is going to make history on Christmas Eve of this year. And when we talk about that time around Christmas and the end of the year, we are talking about gifts and presents. And I'm hoping that the sun will give us the best gift ever. That is one of the strongest explosions ever, that when Parker Solar Probe is very close to it. That will help us tremendously understand these events and their complexity and how they affect the medium it goes through. Many times I was asked about the Carrington event that happened in 1859 that caused the strongest geomagnetic storm in recorded history. And I'm actually of two minds about this. The rational human being in me says, yeah, that's actually can be very serious, and let's not hope one happen anytime soon. But the scientist in me says, you know what? Let's see the show. It's going to be amazing.
Yeah. And, one of the things that's really spectacular about Parker Solar Probe is, for example, this May event, which created this amazing aurora. The eruptions on the sun were not the strongest ones we've had. And to some degree, the analysts predicted a smaller impact here at Earth, and we were all very much surprised. And recent research has shown that part of that is due to certain aspects of the complexity of the magnetic field within the CME and how it wraps through the CME. And it's very difficult to measure that. And right now, we typically can only measure that very close to Earth. Parker Solar Probe can provide this incredible data and incredible detail, not just of that magnetic field, but that magnetic field shortly after it has left the sun. And this is such a game changer to allow us to better understand these solar storms. And part of the benefit for that is someday for us to be able to predict them on the same, sort of the same scale of what we do here on Earth.
Yeah, and for talking about gift giving, I will have my fingers crossed for more aurora over Earth as well. So for folks who do manage to spot auroras, is there any way for people to let NASA know?
Yes, citizen science is a fantastic way. And a colleague of ours, Elizabeth McDonald, created something back in the previous solar cycle called Aurorasaurus. It allows people to report their sighting of aurora via Twitter, or now called X. And that information provides very unique data, which gives us detail on a much smaller spatial scale of where these aurora occur, which is something we don't actually normally have. And so it's really an amazing opportunity for everyone to share in the science and provide this unique data for NASA and our colleagues to sort of understand this really complex phenomenon.
So to learn more, you can visit go.nasa.gov/citizenscience. So we have a lot of questions coming in online. And remember, you can submit yours by commenting in the stream wherever you're watching, or by using the hashtag AskNASA. So Alex and Noor, let's jump in. So our first question is from Al Figueroa on X, and they ask, how many minutes or hours of images and data are we expecting to see?
So for every orbit, we bring down hundreds of gigabits of data. So we have different types of data. We have the imaging, but we have also the in situ that has magnetic fields, electric fields, densities, temperatures, all that data down that Parker Solar Probe gathers when it is close to the sun. We have to wait for it until it is a little bit far away. Then we can talk to the spacecraft and bring it down. So after this encounter that we are about to enter, we have to wait for about 3 weeks. That is a little bit after mid-January, when the geometry is favorable for data downlink, and then we can start talking to the spacecraft and bring the data down.
Fantastic. So we have a question on Twitch from Valikanos, And they ask, how fast will the probe be traveling when it passes that close to the sun due to gravity assist?
Wow. Well, it's going to be traveling approximately 430,000 miles per hour. To give some perspective, if you were to travel from Washington to Philadelphia on Parker Solar Probe, you would make that trip in about a second. So it's just phenomenal, and it's just an amazing piece of engineering again.
Joy and Alex, I'm actually dreaming for bigger distances. And, you know, I was like both of you, I was born after 1969 when we landed Neil Armstrong and the other folks in the moon. And still, when I see it, it's really so inspiring. So, you know, it's huge. We are dreaming of landing women for the first time in the moon by the end of the decade, and also return men to the moon as well. So it will take them about 3 to 4 days to get there. But if you pick a ride on Parker Solar Probe at that speed, when it is very close to the sun, it will take only about half an hour to get from the Earth to the moon. That is extreme. It's really fast.
That's incredible. So we have another question on YouTube from AstroSeeker9. And the question is, how much of the solar corona heating is magnetic reconnection, and what other processes contribute to the overall coronal heating?
So magnetic reconnection plays a big deal into what is going on, because magnetic reconnection by nature it releases magnetic energy to the plasma in the form of heat, but also speed as well. But it also creates a whole spectrum of waves, and some of them that we call the alpha waves, they will propagate very high into the solar corona in the atmosphere. Some of that get reflected, and when the two counter-propagating waves couple, they provide a cascade that will basically bring the energy toward very, very small scales where the particle can absorb them and gets heated and accelerated along the way. And that's actually at least one of the theories that we are thinking that is responsible for the heating and the acceleration of the solar wind. And guess what? Parker Solar Probe is actually guiding us toward what might be the solution to that. And magnetic reconnection is at the center.
Well, I can't wait till that day, since I know it's been one of the biggest mysteries around the sun. So that's really exciting.
Absolutely.
So next, I want to show a video captured by Parker Solar Probe. In 2022, as Parker was making its 13th orbit around the sun, it saw a big eruption known as a coronal mass ejection bursting from the sun. And not only did we see it, but we could actually hear it as well. So let's take a look and a listen. My question to you two is, what are the streaks we're seeing on screen?
So the streaks we are seeing there are basically Parker Solar Probe. When it is flying in space, it is constantly bombarded by dust. And whenever you have dust particles that hitting the spacecraft, it creates debris of spacecraft material that is flying all over the place. And the cameras are actually imaging this debris. And I can tell you, when we launched the mission, we were surprised that some of these images, they are absolutely useless because they are so dominated by these streaks. I mean, you can only see streaks. And, you know, we know that we built a spacecraft and it's returning data that is so exciting. But we were so worried. So how long the spacecraft can survive this? But more than 6 years after, Probe is so healthy. It's doing so well. And it's really so surprising to build a machine that outperform even your imagination, which is fascinating.
Yeah, I'm really glad you showed that image. That's one of my favorites. But the thing that's special for me is actually only recently at a science conference when Noor presented it and then another colleague did. That's the first time I've heard it. at that conference. I had seen the data and seen the imagery, but I had never heard it before. And Parker Solar Probe has also provided a lot of other data, including some of these waves that Noor was talking about, which we have now used sonification. And it's really amazing, not only to see the data, but to hear it.
Absolutely.
So Parker Solar Probe has been traveling for about 6 years to the sun. What are some other interesting things Parker's seen on its journey?
Why don't you start, Alex?
Can I? Oh, sure. Actually, there's a couple of things. That particular video is one of them. Related to that is some data showing a coronal mass ejection, which is passing by the spacecraft, but also clearing out the space, clearing out all the particles, including the heavy particles, basically providing a perfect vacuum. And that's one of my favorite types of data, and an amazing observation. And the other one that I'll bring up is Venus. So, Parker Solar Probe has used Venus on 7 flybys to use the gravity, a gravity assist, to slow the spacecraft down so they could get closer and closer. But that was also a unique opportunity to take data observing the planet, and the WHISPER instruments, which are those very sensitive cameras with the imagery you just saw, were able to, for the first time, see through the atmosphere of the planet to show features on the surface below in visible and near infrared light. And looking at that next to radar, those particular features line right up from earlier observations many decades ago.
When we got this data from Venus, that it's really, these images are spectacular. So the program we set up back then is basically to look for clouds in the atmosphere of Venus. So, and when we saw these dark patches, we thought, yeah, these are images of the clouds, and we were kind of excited, but we were nervous. We are not Venus people, so only to discover that a Japanese mission, Akatsuki, almost have exactly the same image that was back even before we launched Parker Solar Probe. For us, it was kind of disappointing. And I showed exactly the same data that we saw at one of the seminars I gave, and told the story as I said it now. But the folks who are Venus specialists here at the Johns Hopkins Applied Physics Lab, they were so excited about that data set. And we gave them the data, they looked into it, and guess what? They actually learned about the composition of rocks on the surface of Venus. And on top of that, they discovered a new window to study the surface of the planet. Parker Solar Probe now holds the shortest wavelength thermal emission from the surface of Venus. It's a record. Previous records, they have been about 1 micron and 1.58 micron. Parker Solar Probe, with this new window, holds the record of 0.75 micron, and the future mission for Venus will actually exploit this. Since you mentioned, you asked, and then this is really goes into the science of the mission. And from orbit 1, when Parker Solar Probe flew close to the sun, we observed folds in the magnetic field that we call them switchbacks. Basically, the magnetic field will roll all the way back to the sun and out again, forming an S shape. And when we saw them the first time, and it was a Tuesday, and we were supposed to share that data for the first time with the public on a Thursday at the American Geophysical Union. And for the first time when we saw it, we thought, yeah, there is something wrong with the instrument. And that was a really bad feeling. We have been waiting for this mission for 60 years. And if the first thing you get is really a problem with the instruments, that's pretty bad. So it took us probably something like 15 minutes to do some checks on the data, and everything checked out. What we are seeing is something new. And guess what? These switchbacks that Parker Solar Probe observed in abundance close to the sun, they actually guiding us toward understanding what hits the corona and what accelerates the solar wind. It's kind of fascinating. It's really amazing.
So we have more questions coming online. So let's get to more of those now. So a viewer on X asks, how will the probe act when a sudden coronal mass ejection or magnetic storm occurs during the flyby?
That's a really great question. Let me start by saying this. When Parker Solar Probe is flying close to the sun, we cannot talk to the spacecraft. So it has to be 100% autonomous, meaning it has to deal with any issue that it might encounter. And actually, the autonomy system that is built on the spacecraft can drive the vehicle for nearly 2 months without any intervention from the ground. And actually, we did that twice already. Now, Parker Solar Probe is designed to fly through this big explosion that are coronal mass ejections. And actually, we flew through dozens of them. And for the one that we showed earlier, actually, we see a tiny bit of momentum transfer to the spacecraft, but it is so low. And Parker Solar Probe obviously dealt with it without any issues at all. So that's why I said earlier, the sun, please do your best. Give us the strongest event you can do, and let Parker Solar Probe deal with it.
A lot of viewers are very intrigued that Parker Solar Probe can get close to the sun without melting. And I know we touched on it before, but can you tell us a little more about the technology that enables this spacecraft to get so close to our star?
Yeah, why don't you talk about this? I brought it up earlier, so why don't you go ahead?
Sure. Obviously, Alex brought up the heat shield earlier, which is, I have a sample of it here. So, and the heat shield is basically what enabled the whole mission. It's a piece of carbon foam that is 4.5 inches thick. We have a ceramic coating on top of it. It's white for a good reason, to reflect as much light as possible. So when we designed the heat shield, we designed it for temperatures to withstand temperature that are in excess of 2,500 degrees Fahrenheit. To our surprise, actually the heat shield is cooler now, and we are expecting only temperature of about 1,800 degrees Fahrenheit on December 24th. On the back side of the heat shield, that is 4.5 inches back, the temperature will be about 500 degrees. And about a yard later, it's almost room temperature. And the heat shield is basically what stands between the probe and the sun. Everything has to fit within the shadow cone of the heat shield and to operate at room temperature, except a couple of sensors that are electrostatic antenna and also a solar wind instrument. Obviously, Parker Solar Probe has the right to wiggle a little bit like any spacecraft up there, but the tolerance for us, it's only a small fraction of a degree. And to maintain the attitude of the spacecraft, we use 4 subsystems that together have to work together to keep the spacecraft looking squarely at the sun. We use momentum wheels, we use thrusters, we use single cell cameras that we call them the limb sensors. I will come to them in a minute. And also we have star trackers that are looking at the back of the spacecraft, looking at the sky for the star field, basically to tell the spacecraft where it is located. For the limb sensors, this basically will detect the edge of the sun whenever Parker Solar Probe deviates a tiny bit. And this will send a signal to the computer to start basically correcting the attitude of the spacecraft. But all these 4 subsystems have to work together to maintain because if we don't do it, we can lose Parker Solar Probe in no time at all. The environment is so harsh. It is not forgiving at all. And yeah, so far, Parker Solar Probe is really doing a great job.
So Matthew on Facebook asks, how long will it take Parker Solar Probe to complete the 22nd perihelion, or the 22nd orbit around the sun?
Well, we are almost about to enter what we call the encounter, which is the part of the orbit when Parker Solar Probe is below a quarter of an AU. And it's just a few days from now. It takes about 11 days to cross the sun from one side to the other side. But when Parker Solar Probe is very close to the perihelion, the closest approach to the sun, it is zipping through longitudes. It can cover over 150-degree longitudes in a couple of days, which is fascinating.
That is fascinating. So Victor Swenson on YouTube asks, how is the probe protected from gamma rays, and what type of substrate is used on chips?
Go ahead.
for gamma rays and the intensity of gamma rays is not really that high, and we don't have any specific shielding for it. But we have enough shielding in the spacecraft for radiation from the sun, because we want to protect our electronics. And most of the electronics are actually within the bus, that hexagonal structure that is at the in the back of the heat jet, in the back of the spacecraft. All the electronics are there within that structure, and we have enough shielding. But also, when we were designing the spacecraft, we had to make sure that we don't really overload the spacecraft, that it becomes too heavy. So it's really a balance between the two, that the spacecraft is protected, but also to remain light.
And I could also add that gamma rays on the sun, that's something that I studied, primarily come from solar flares. They're not as common. And we've done a lot of studies about sort of the background sun, and the gamma rays, for example, that are created in the core never make it out, because those are eventually turned into the visible light photons that we see here on Earth. So gamma rays are not particularly intense. Unless you're sitting right on top of a very large solar flare, you don't have much to worry about.
Yeah.
So a viewer on Twitch asks, other than shielding, what are some of the challenges of navigating in the vacuum of space at temperatures much warmer than a few degrees Kelvin?
So one thing about the medium that Parker Solar Probe is flying through, and it is multi-million degree hot, that we know it, it's the corona and the solar wind, but there is one aspect of it. It's very tenuous. The density is so low. So when Parker Solar Probe is flying through it, the gas itself does not really transfer that much heat to the spacecraft. So that's why Parker Solar Probe, we have only to protect it from the radiation that is coming from the sun. That's the main reason we want to protect it. Obviously, there is always risk that the spacecraft will encounter issues there. And we have seen it when probe is around the sun. For example, star trackers, oftentimes they turn off, but they turn them, the autonomy will turn them back on. So again, we rely on the autonomy system to guide the spacecraft when we cannot talk to it. We have all sorts of solution to almost all sorts of problems that the probe can go through. And so far, everything was really going fine.
And yeah, and I'll add to that. So Nora's talking about how tenuous the corona is. This is a pretty interesting thing that we love to talk about, because it tells us about the difference between temperature and heat. If you actually were to take a cube, about a meter cube, and fill it with the corona, you would have maybe just a few particles inside that box moving around. Now they're moving super fast, which is they're moving to give them a temperature equivalent of many millions of degrees. But because there's only a few, there's not enough particles to really transfer any energy, which is the heat part. And as he mentioned, it's really the light radiation coming from the sun, which is so incredibly intense, that we're concerned about.
I love that.
If there is one thing, just a small thing that I really want to point out before I forget it. So yeah, the focus is on the sun, our star. But the phenomena that we are studying here, they are not unique to the sun. We see them in billions and billions of stars out there in the universe. And basically, by having this close look at our star, we will also learn about other stars in the universe. And in particular, now we are so interested to know if we are alone in this universe. Basically, we are looking for life elsewhere. We want to understand how Earth is really so. Is it really so special that we are unique, or we are unique? And also, whether the sun then the sun can enable life elsewhere in the solar system as well. That's also another aspect.
Yeah, and this is one of the reasons why we study the sun. The sun is the only star that we can treat as a laboratory. It's the only star that we can see in detail, but we can actually go to and measure it directly. and that's one of the reasons that I started studying the sun, is it's a laboratory in our solar system that allows us to learn about all the other stars in the universe and how all those stars interact with the billions and billions of other planets that may or may not be like our own planets in our solar system.
Exactly.
So Johnny on X asks, how do you communicate with the probe at its closest approach to the sun?
Yeah, when we are very close to the sun, actually we cannot talk to the spacecraft at all. The spacecraft every now and then talk to us, and it's so limited. So when we are going toward the sun and the way in, at a certain point, Parker Solar Probe will send us what we call the beacon tone. And the beacon tone is really a very limited piece of telemetry that tells us the overall state of the spacecraft. And so far, we got only green beacon tones, which is basically a synonym of the spacecraft is its nominal state. And also on the outside, we will get another one. So for this encounter that we are about to enter, on December 22nd, we will get the first beacon tone. And after the closest approach on the night of December 26 to 27, around midnight, we will get the other beacon tone that to tell us how Parker Solar Probe did during this closest approach. Other than that, when it is during the encounter, we cannot talk to it at all. We cannot do anything to it at all. But when it moves far away, then we have the high gain antenna. We can actually orient it toward Earth, and we can talk to the spacecraft and get data from the spacecraft, but also upload commands to the spacecraft.
Yeah, that's one of the things that makes these kind of missions, not just going around the sun, so difficult. And because it's far away, as they get farther away, also the signals are weaker, and it makes it a challenge. Flying spacecraft is not easy, and engineers are amazing.
And we are really thankful for the DSN folks who are doing really an amazing job. Whenever they bring us a lot of data with communicating with the spacecraft, but also when there are emergencies, they really step up and provide us the support we need to deal with them.
Yeah, the DSN is
the way,
Deep Space Network, which is something we use for really distant missions like Voyager, New Horizons, and then some of the other solar missions like Stereo at SOHO, for example.
Yeah.
So I have another question on X from Christopher Casey. And Christopher asks, will solar wind ever be used to drive spaceships?
Oh, that's a good one. That's a really good one.
Really good
I'll start with this one. Yeah. So, there are something called solar sails. So one of the ideas is with solar sails, actually using momentum from light or from particles, but because space is so big and there's so few, these solar sails, to be practical, have to be incredibly big, maybe the size of many, many square kilometers. But I will say I've actually read some papers about technology to create a giant solar sail to actually use the solar wind to generate electricity. Now, it's certainly not something that's practical for us right now, but it was a really interesting concept.
Yeah, to that point, Alex, there are certain companies out there. They are looking for harvesting basically the gas that we are flying through. In particular, when you're flying away from the sun, in particular for producing nuclear power or things like that. So there are ideas like that. The technology might not be mature for now, but that's really something for the future that we have to look up for.
So Jaredon on Twitch asks, which of the 4 instrument suites will see the most intensive use this perihelion, or will they all be equally used?
All of them. All of them.
Yeah.
I mean, we have the imager that is Whisper, that provides us with images like the ones we saw before. We have the field suite that basically measure magnetic fields, electric fields, densities, waves, fluctuation, radio emissions. We have the suite which measure the solar wind, that are electrons, protons, and helium ionized twice, that we call alphas. And also we have the ESIS instrument suite that measure these energetic particles that we talked about earlier, these are very high energy particles. So all of them will work together to provide us with basically a picture for the whole medium we are flying through.
Yeah, I mean, it's one of the important things about science missions. For most of them, when we look at the universe, we have to look at different particles, different types of light. We can't just look at a single thing to get a bigger picture of what's really going on. And this is especially the case here for studying this very complex region. We have to have a lot of different types of information. All of those together are pieces of the puzzle. Otherwise, we're really missing out on a whole lot of information.
So let me add to this. We are so lucky to have launched Parker Solar Probe in 2018. About a little over a year later, we launched Solar Orbiter, which is the ESA NASA mission. And about a year later, we also got the largest solar telescope in Hawaii also start operating. So these trio together, they form they form a golden era to study for the heliophysics and to study the sun. But let me add one thing. I think it was the third orbit of Parker Solar Probe. And when I put an announcement out there, basically soliciting observatories to volunteer their time to observe with us when Parker Solar Probe is flying by the sun. And my hope back then was, basically we'll get a handful of them to observe. Guess what? We got over 50 observatories between space and Earth that volunteered their time to observe with us. And since then, for every orbit, we have this campaign that is ongoing. My expectation for the closest approach will break that record of 50 observatories. I'm hoping for more than that.
So we have an interesting question on Twitch. What do we hope to learn about other stars in the process of investigating our own sun?
I'll start. One of the things that's important. Well, a lot of the aspects of what Parker is measuring are ubiquitous with other stars. However, stars vary. They vary in size, they vary in age, and so some of the details are very different. Many stars have a wind like the solar wind. We call them stellar winds. There are some that do not. There are some that have incredibly violent stellar winds. But one of the things that I think is, for me personally, I think is one of the most critical ideas is better understanding magnetic reconnection. Magnetic reconnection is the way that we know of that nature is able to convert magnetic fields into energy. Magnetic fields contain energy, but converting that into energy that nature can actually utilize is quite difficult and quite complicated, but it happens all through the universe. It happens around the Earth in its magnetosphere, which is the reason why we launched the magnetospheric multiscale mission, or MMS. It happens at the sun with things like the solar wind, with things like coronal mass ejections, with solar flares, but it also happens around black holes. It happens around different star systems that eventually become types of supernova. So it's really important. It happens everywhere on different scales. And that's one of the reasons that what we're learning from Parker Solar Probe is so critical for understanding fundamental physics across the entire universe.
If I add something to that, and Alex basically said it all, so I think one of the top questions that in the minds of everybody out there, is basically whether we are special in the whole universe, whether we are unique. And if we are not unique, how life can develop around other stars. And we have our sun, which is just in our neighborhood here. We want to understand how it shapes its star bubble that we call the heliosphere, and how it really kicked life on Earth here. How it did that. But more than that, we recently launched NASA launched another mission, that is the Europa Clipper, to study the Europa moon, that is one of the moons out there that has the potential to have an ocean below the ice, and might harbor life. And pretty soon, we will launch another exciting mission, Dragonfly. It will go to Titan, that is a moon of Saturn. And that is going really to look at chemistry, to look at different aspects that might be relevant to life there. Basically, we started looking at signature of life elsewhere. So it comes to, at the end, how the sun interacts with its planetary system and where it can potentially kick life there. We know it. We are here on Earth. We know that's for sure, and it's the only place on the universe we know there is life, and that is us and other. But also, we want to understand elsewhere. And again, what we learned from Parker Solar Probe and other missions is so critical to achieve that.
So Rick Weber on X asks, what is the most perplexing question about our sun that NASA would like to answer through this probe?
That's a tough one.
There are so many of them. It's not, there is no shortage of them. You know what, Alex? I will start with the interior and we move out. So if I start with the interior, first of all, we have absolutely no idea how the core of the sun itself works. We know there are thermonuclear reactions that are ongoing there, and that's actually what produces all the energy that the sun uses to do everything in the solar system. But if you move above, we also know that all the magnetic fields that we are talking about, they are actually generated in the interior of the sun. And the funny thing is that they are generated in a cyclic fashion. We have what we call the solar cycle that is 11 years long. We go from a period when the sun is very quiet, like 2018 when we launched Parker Solar Probe, to a maximum when the sun is very active, like it is now, and when we move again to a period of minimum again. And this is not all. The sun, every now and then, every about 200 years or 300 years, will go through an extended period of tranquility, like the Maunder minimum that occurred in the 1600s, 1700s. And when it goes very quiet there, it affects our environment, for example, really, really big time. Like the mini ice age that occurred in 1645, 1715. Actually, the sun at that time was very, very quiet. So this variability of the sun, it's all driven by that magnetic field that is generated in the interior and rises up to the atmosphere and do all these phenomena that we want to understand. Alex.
Yeah, and so this process that Noor is referring to, we call it a solar dynamo. And it's a very important physical process. In fact, the magnetic field of the Earth is generated in a very similar way. The Earth has a liquid, metallic core. So any object that's liquid or some sort of substance like the sun is made of, called a plasma, these have the properties of liquids and solids, but they are electromagnetic in nature. They respond to electricity and magnetism. And when they spin, they don't spin equally, just like the planet Jupiter or Saturn, which makes those striations in it. And that produces this magnetic field, this dynamo. And it's incredibly complicated. And right now, we have computer models that can somewhat produce what we see with the sun, but we can't quite figure out, for example, why is it 11 years? Why is it not, 15 years? We see these cycles on other stars and they have different lengths. So this is one of the key pieces to the sort of fundamental nature of a star, of our star in particular, that we do not fully understand, and we have a long way to go. Maybe once we understand it, we might be able to make real robust predictions of the solar cycle, the next solar cycle. Will it be big? Will it be small? Will it be longer or shorter? that would be part of the goal of that. But this is just a huge, outstanding problem that will probably be one of the biggest discoveries, if that is solved in our lifetime. And that connects to all of the things that are happening at the surface and in the corona, which are what we're learning about from Parker Solar Probe.
So talking about the atmosphere of the sun and the corona, we have all this activity that we talk about, like flares and coronal attraction. And by the way, oftentimes we talk only about the big ones, but it's really a whole spectrum. They occur at all scales, and even the smaller ones are extremely important. Now, they are the drivers of space weather that we see here on our environment every now and then. And we need really to aim for reliable predictions of what the sun is about to do at any time. Our prediction capabilities of space weather are about maybe 50 years behind the prediction of weather on Earth, but we are getting there. So at a certain point, we will be able to predict the space weather like we predict weather. But let me say this. Oftentimes, when we talk about the solar activity and what it does to our environment, we kind of give it a negative meaning, that it's really harmful, it is really sad, it is gloomy. And guess what? Without that activity, we would not exist. That activity is really necessary for life to kick off wherever it has to kick off around the star. So in a way, the sun is really our reason to exist. But it can also affect us in adverse ways. So we have to find a way how to live with it in harmony. And the best way is to understand it, and to understand it through missions like Parker Solar Probe.
All right, so we have time for one final question, and this is for both of you. Can you quickly tell me, what advice do you have for viewers who might be interested in helping NASA study the sun?
Well, I would say one way to really help NASA would be to participate in citizen science. Citizen science, we can look at everything from extrasolar planets to aurora to solar flares. There are all sorts of different aspects of Earth and space science that NASA studies, and there are a huge number of citizen science projects. All of them provide data that is really important and in many ways critical for NASA, and something that we could never get on our own. And if you participate, you too will be a scientist and helping us to discover and understand the world we live in.
So to everybody out there, and I'm mainly addressing the younger generations that are coming, from babies all the way to students. If you think that Parker Solar Probe is very complex, or James Webb is very complex, guess what? Now we are looking for missions that are way, way more complex than that. If you think of, for example, for the sun, the goal is no longer to launch a single spacecraft. We are aiming to launch constellations. And when we are talking about constellation, I don't know how many birds we are talking about. And this is really all up to you to do it. So my advice to everybody out there, be curious, be bold, be adventurous. And guess what? We don't only need engineers and scientists. We need all sorts of knowledge. We need scientists, we need engineers, we need financial people, we need lawyers,
doctors, we need everything. Yeah,
we need everything. You cannot imagine to build a mission so complex. You need thousands of people to build it. It's not really only the couple of us who are speaking here who basically came together and put it together. It's really take an army to build a mission like Parker Solar Probe.
Yeah, every single person is really critical, and it takes a team, and that it will always be that way.
Absolutely.
That is great advice. Thank you both so much for joining us to discuss this incredibly important and interesting topic.
Thanks for having us.
And thank you to everyone watching online. To stay updated on sun science, follow NASA Sun Science on Facebook and NASA Sun on X. We'll be sharing updates on those channels as well as NASA's website about Parker Solar Probe's closest approach to the sun. So stay tuned. Another way you can participate in NASA Sun Science is through our puzzle quest. As we mentioned earlier, today is the start of a 3.8 quest, and we're challenging you to solve our puzzles as fast as you can to find hidden web pages and custom 3.8 digital stickers. Thank you so much, and see you next time.